Okay, so in today's video, we're going to be looking at the idea of an absolute maximum and minimum value of a function. In the previous video on stationary points, we talked about the idea of a local minimum stationary point or a local maximum stationary point without really referring to that word local. So we're looking here at that distinction between a local minimum or maximum point versus an absolute minimum or maximum point or value. So a local min or max is it's a local maximum, it's a maximum turning point within its local neighborhood. Okay, so for example, this point here, that's a local maximum. Okay, it's got a within its neighborhood, it's the maximum value. Okay, locally it's the maximum. However, globally, if we're thinking about this whole entire function f of x, that is certainly not the maximum value of the function. Okay, the graph gets higher and higher and higher here. There is no maximum value. The graph approaches infinity. Similarly, this point here, that's the local minimum turning point. The local minimum value is 0, but that is not the absolute minimum value of this function. The graph gets lower than that. It doesn't actually have a defined minimum. Its minimum is negative infinity, which we wouldn't actually say. So f of x has a local minimum at the point 2/3, 25/27, but 25/27 is not, sorry, a local maximum at that point, but 25/27 is not the maximum value of the function. Okay, there are higher points on the graph than that. An absolute maximum is the maximum value for the function in the interval for which it's defined. So this maximum won't necessarily be at a stationary point, it might be at an end point. Okay, so formally m is the absolute maximum value of a continuous function over the interval a to b if f of x is less than or equal to m for all x values a to b. Okay, so let's say, for example, let's restrict this function. Let me just get a thicker pen here. So let's say if I restrict this function to, let's say that's a, okay, and this is b. Okay, so in this case we can see clearly that the absolute maximum value is going to be that. Okay, so it will happen when x equals b. Okay, that will be the maximum. So using this definition here, that would be m. Okay, now that's not a universally understood notation. You wouldn't just write capital M to mean absolute maximum value for any function unless you've defined it, but it's defined in this sentence. So m is the absolute maximum value if over the interval a to b if f of x is less than or equal to m for all x values, and that is true. The value of the function is less than or equal to that value of m for every x value in this interval a to b. Okay, the whole function is below m. If you were to draw the line y equals m, the whole function, sorry, the whole green function would sit on or below that, which it does. Okay. Now, if n is the minimum value, so in this case, let me draw that back in. Sorry, I lost my curve. Let's say that's a. In this case, the minimum value would be when x equals a at that endpoint, because the whole function sits on or above y equals n. Okay, f of x is bigger than or equal to n for all x values between a and b. So that's a fairly intuitive definition. I wouldn't worry too much about that kind of formal definition. It makes sense. The value, y value is the maximum value if the entire function sits below that maximum value or on that value. Sorry, slightly convoluted today. Okay, so let's have a look at some examples. Let f be defined over the interval -2 to 7, inclusive of -2 and 7, such that the rule for f of x is 2 minus x squared. Find the absolute maximum and absolute minimum value of the function. Okay, so we need to actually think about this function. You really need to be able to see the graph. You need to draw the graph. It doesn't need to be perfectly precise, accurate, every single point drawn, but you need to have a sense of what is happening with this graph and where will the max and min be. Okay, so the function is 2 minus x squared. So that is a reflected parabola, negative x squared, translated up by 2. Sorry, just let me draw my x-axis. In fact, I'm going to draw it higher again. Alright, let's say that's 2. So here is my parabola. I draw it wider than that too. Okay, let's say we've got, now it is defined from negative 2 to 7. Okay, so when x equals negative 2, y will be equal to 2 minus 4, so negative 2. Okay, so we're going to be at negative 2, negative 2, okay, inclusive of that point, up around the turning point, and then we go to x equals 7, which is going to be way off the charts down here, but let's just get a sense of what's happening. When x equals 7, we'll have 2 minus 7 squared, 2 minus 49, so that's negative 47. Okay, so thinking about this function, it's really clear that the lowest possible point, so it's the red graph, the lowest possible point here is that's the minimum, and the highest point is up here, that's the maximum. So find the absolute maximum and minimum values of the function, so it's the y values we're after, okay? So the absolute minimum of f is equal to negative 47, and the absolute maximum of f is equal to positive 2. Okay, so if we've got g, it's a cubic function, restricted domain, sketch the graph and state the absolute maximum and minimum values of this function. Okay, let's think about the cubic. It has got x-intercepts at 0 and 3 with a turning point at 0. It goes from negative 2 to 4, so let's just work out those endpoints so we can get scale a little bit better than we did in the previous one. So f of negative 2 will be 4 times 3 minus 2, 4 times 5, which is 20. F of 4 will be 16 times 3 minus 4, negative 1, so negative 16. Okay, now we have got, sorry, just thinking about what we're having here. So if domain is negative 2 to 4. So negative 2, positive 2, 4, negative 2, 20, negative 2, negative 2, 20. We're going to have a turning point at 0, 0. We have another x-intercept at 3. It's a negative cubic, so it goes in this direction, which makes sense given all the other information we've calculated. And that will be 416. Sketch the graph and state the absolute maximum and minimum value. So we actually don't need any derivative for absolute max and min, because whilst this has 2 stationary points, well actually we probably do need to technically work out, I've drawn it that doesn't go higher than 20, but actually, you know, what if it does that? So we do need to just make sure that we definitely know that the other turning point is at 0, 0, so the minimum is going to be at 16. So we might just quickly find the turning points. So g dash at x, let's expand first. So g of x is 3x squared minus x cubed. G dash at x is 6x minus 3x squared. That equal to 0. Factorising. And so we get stationary points at 0 and 2. We already knew about the one at 0. We're interested in the one at 2. So g of 2 will be 2 squared, which is 4, times 3 minus 2, which is 1. So 4. So that point there is at 2, 4. That's at 0, 0. So with a complete sketch of the graph, that intercept, given the question asked us to sketch the graph, your graph sketch should be, more accurate than if you are by choice choosing to sketch the graph to help you answer the question. So we've got our sketch of the graph, all intercepts, turning points and endpoints marked. That's actually the other thing to note. Now that we know how to calculate stationary points, in sketching a graph, you should always have stationary points marked. Okay, so we know now that the minimum value of f is going to be 16 and the maximum value of f is going to be 20. So minimum and maximum in this instance happening at 2 endpoints. But you can't make that assumption. In the previous example, the maximum value wasn't at an endpoint, it was at a stationary point. Okay, example 3. For the variables x, y and z, it's known that x plus y is 100 and z is x over y. If x is between 22 and 45, find the possible values of y. Okay, so thinking about the connection between x and y, we know that y equals 100 minus x. Okay, and so thinking about that relationship, I mean, you can think about the graph. It's clearly a straight line with negative gradient, gradient of -1 and y-intercept at 100. So it's going to look like that. So if we're only looking at the domain where x could only be between 22 and 45, we're only looking at inclusive, we're only looking at this bit of the line, okay, 22 to 45. And so it's clear that the maximum value of y happens when x equals 22, and the minimum value of y happens when x equals 45. So we know maximum y is going to be at 100 minus 22, which is 78. And we know that minimum y is going to be at 100 minus 45, which is 55. So possible values of y is an element of 55 to 78. The absolute maximum and minimum values of z. Okay, so z equals x over y. Okay, so z is going to be equal to, we could think about this in a couple of ways. So we know that x is equal to 100 minus y. So that means that z is equal to 100 minus y over y, which is 100 on y minus 1. Okay, so thinking about that, that's a dilated hyperbola. So this graph was x versus y. Now this graph will be y versus z. So it's a hyperbola down by 1. But again, with that restricted domain, only from 55 to 78. So it's a dilated hyperbola down by 1. It doesn't really matter where the x-intercept is. Again, I'm not being asked to sketch the graph, but we're only looking at it over a domain from 55 to 78. Okay, so if we think about when y equals 55, we're going to get z equals 100 on 55 minus 1, 1 being 55 on 55. So we get 45 on 55, which is 9 on 11. And when y is 78, z will be 100 on 78 minus 1, which is 78 on 78. So it'd be 22 on 78, which is 11 on half of 78 is 39. Okay, so we've got, now I probably should have drawn my graph a bit. That x-intercept is going to be a long way away because of the big dilation. So you've essentially got, you're essentially looking at the graph only between so this axis, the horizontal axis here is y, the vertical axis is z, my graph is z in terms of y. We're only looking at this graph between y equals 55 and 78, and we have just therefore calculated that when y equals 55, z is 9 on 11, and y equals 78, z is 11 on 39, and so the absolute maximum is 9 on 11, and the absolute minimum is 11 on 39. So generally speaking, minimums and maximums will be at endpoints or at turning points. So you need to make sure you're thinking about endpoints. It's in conjunction with turning points. Okay, find the maximum value of this expression. Okay, so if you think about, if we say we're going to let f of x equal 100 e to the negative x squared plus 2x minus 5, we're being asked to find, maximum f. Okay, so maximum value of the function. So again, we need to think about what this looks like. Now, we don't know what this graph looks like, so therefore we want to think about where are the stationary points to help us here. It's not got a restricted domain at all, so we want to think about station. It's probably going to be at the stationary point, so let's show that. So derivative here is going to be, the 100 has no effect on your derivative, e to the negative x squared plus 2x minus 5, so we're using chain rule. E to the derivative of e to the something is e to the something, and then we multiply by that derivative of the something, which will be negative 2x plus 2. Okay, so let's see what we've got here. Let's take out 2. So we're going to have 200 times, that'll be negative x plus 1, so I'll write that as 1 minus x, e to the negative x squared plus 2x minus 5. We want that to equal 0 for our stationary points. So 200 can't equal 0. 1 minus x could equal 0, so x equals 1. E to the negative whatever can't equal 0 either. An exponential can't be equal to 0. So we have one stationary point when x equals 1. Okay, let's work out the coordinates of that stationary point. So f of 1, so it's going to be 100 e to the negative 1 squared plus 2 times 1. So negative 1 squared is just... Now be careful about that. That's negative x squared, which means negative 1 times x squared. Okay, so it's still going to be, when x equals 1, it'll still equal negative 1. So we're going to have negative 1 plus 2 times 1, which is 2, minus 5. And so we have 100 e to the, what have we got there, negative 4, or 100 on e to the 4. However you prefer to write that is fine. Okay, so we've got our stationary point. So we know there is a stationary point. In order to answer this question, it's going to have to be a maximum stationary point, but we don't know that, and we can't just draw that assumption. So let's use our sign diagram. So let's think about our x values, the value of our derivative, and what that means for the shape. Okay, so our stationary point happens at 100 over e to the power of 4. The derivative at that point is 0, therefore we have a stationary point. Now we want to think about somewhere to the left and somewhere to the right, and a smaller x value and a bigger x value. So obviously 100 over e to the power of 4 is positive, and we've only got the one stationary point, so we don't have to stick super close to that stationary point. We're either going to have positive gradient before it and negative after it, or, well, it might be an inflection. But the point is that because there isn't a second stationary point, we don't need to sort of stay super close. So somewhere to the left of this, 0 is definitely smaller than this. So let's sub x equals 0 into this. So that will give us 100e to the negative 5. Okay, 100e to the negative 5, which is 100 on e to the 5. Small, but it's still positive. Okay, and then a number bigger than 100 on e to the 4. Okay, so e is about 2.71. So let's say it's about 3. Okay, so 3 to the power of 4 is 81. So it's 100 on 81. Okay, so that's roughly 5 on 4. So you could definitely go, I mean, 2 might be a bit close, just in case you haven't estimated. So just pick any number that's bigger than kind of 2. I don't know, let's go with 3, or maybe 5, or you could even go with 10 just to be sure. Okay, 10 is definitely bigger than 100 on e to the power of 4. Alright, so that means we're going to have 100 e to the power of, so we're subbing it into our, sorry, I've subbed into the wrong one. My apologies. Let's fix this. So we need to sub into the derivative. So putting 0 into the derivative, so 0 in here, we're going to have 200 times 1, so that's still 200. So we'll have 200 e to the negative 5. My apologies. 200 e to the negative 5, still a positive number. It's 200 on e to the 5. Okay, let's put 10 into this. I decided. Okay, so 10, 200 times 10 minus, times 1 minus 10, so 200 times negative 9 is going to be negative 1800. And then we're going to have e to the power of, so 10 squared is 100, so it's negative 100, plus 20 is negative 80, minus 5, so e to the negative 85. You don't have to pick 10, you can pick another number. You just want a number that is bigger than 100 on e to the 4. So, you know, I picked 10 to make sure it's bigger. So this is negative 1800 on e to the 85. So the negative at the front means it's negative, and so we've got downward slope. Okay, so therefore we have a local maximum at, so this tells us that we have a local max at the point, what were the coordinates again? 100 on e to the 4. But only one stationary point means 100 on e to the 4 is absolute maximum, and so therefore max value, so the graph doesn't get any higher than that point, max value has to be 100 on e to the 4. Okay, so if you only got one stationary point and it's a maximum, the graph doesn't get any higher than that value. Okay, so that becomes your absolute maximum value, and therefore you've got the absolute maximum value as 100 on e to the 4. Okay, here's some instructions about using function min and max, which we've talked about previously. Again, it gives you the x value, but it will give you the absolute min or max, so that's why it's not helpful if you're trying to find coordinates of stationary points. But if you're trying to find the absolute minimum or maximum value, it can be helpful because it will consider the stationary points and the endpoints. So obviously what you see here is if you don't give it any restriction, it's quite possible the function min or max could be negative, could be infinite, but adding a restriction, same way we would for any other function, given that outside of the function. So looking at here, if we're looking at the absolute maximum, or the maximum of that function, that quadratic function, given that x is between 0 and 4, it tells you that that maximum happens when x equals 4. If you then want to find the absolute maximum, you would need to sub 4 actually into the original function. Okay. All right, the work today is from exercise 10e, so still working around the idea of stationary points, but adding this idea that the maximum value of the function might not actually happen at the stationary point.